Hello everybody, Thy Lord Root here, and today I have a very special treat for you. You see, not only do I have a Pi Day lecture, but I also have an excuse for drinking. And so for those of you who don't know, today is not only Pi Day, but it's kind of a special Pi Day. Because if you live here in the US, then you will know that when you write out the date, it's 3/14/15, the first five digits of pi. Incidentally, it's also a Saturday, and people like to go drinking on Saturday. And so we might show you a fun barroom activity that in reality you probably shouldn't try because you will probably end up with alcohol poisoning. But nonetheless, it's an interesting thing to muse about. And before we do that, I think a real brief history of pi is in order. So let's just talk about some approximations of pi. In fact, there's one in a holy book, believe it or not, in the Old Testament, in First Kings. There is a verse that describes the construction of a bronze fountain. And in this verse, we basically get pi as 30 cubits to 10 cubits. So that is, an integer, which we of course know is not the case for pi, right? Pi is not an integer quantity. It is incidentally better than some of the measurements made in the past, and even in the recent past. I believe in the 1850s, some guy actually tried to legislate pi at a value of 4 so he could square the circle, so he could cheat using legislative fiat. Needless to say, the scientific and mathematical communities did not really take him that seriously. But anyway, you look at this and you say, okay, well, there's at least an error of 1.4 cubits, right? A little bit more, in fact. I don't really think the Hebrews can be held accountable to this, though, for a number of reasons. First of all, this is a theological book, not a mathematics textbook or a scientific textbook or manual. And so you really would not expect precision to be on the top of the author's priority list. On top of that, there's some debate how old the Old Testament is. And again, I don't want to get into a theological discussion about this because this is outside of my realm, so to speak. But, discounting the documentary hypothesis and all of that, we can assume that this is fairly early and that the Hebrews might not have had a very good understanding of the concept of real numbers. So they could be forgiven for that, I think. However, many other civilizations in antiquity did. And so, for instance, if you look at the Great Pyramids of Giza, or the Great Pyramid at Giza, rather, and that was built around 2600 BC, it has a perimeter of 1,760 cubits and a height of 280 cubits. And if you take the ratio of those, you get approximately 2 pi. Also, we have several recorded rational approximations of pi. So there is a Babylonian cuneiform tablet from 1900 BC, and that yields a figure of 25 over 8, which is about 3.125. And about 50 years later, we have the Rend or Rind papyrus. I'm not quite sure how to pronounce that. But then it says that pi is 16 over 9 squared, and that's much closer to the pi we know. Now, of course, pi is not a rational number. We know now that pi is a special kind of number called a transcendental number. But it is actually rather interesting that there was an irrational approximation of pi in antiquity, only it was in Indian antiquity. So I'm going to butcher this name. If you speak Sanskrit, which I'm sure many of us don't. Don't get angry at me, or I guess it would be Hindi, but I think the title of the work is Shweba Sutras. That was written about 600 BC, and it says pi is approximately equal to the square root of 10. And so these are fairly close approximations. They're off by maybe 1 or 2%. But really, we got a much better idea of what pi's value might actually be from Archimedes. And Archimedes of Syracuse is known for a number of things. For instance, Archimedes' principle. And perhaps you might have heard of the Archimedes screw, which is a little device that's used to move fluids upwards. But some people, they may not be as familiar with Archimedes' method of exhaustion. This is a crude form of a process known as integration, where you're calculating the area under a curve. And so the basic idea here is that you have a circle, right? Let's say that the circle circumscribes several triangles that are, let's say that they're of equal area. Well, by reducing the angle near the center on the triangles, then what you will find is that you can fit more triangles in and get a better approximation. And of course, Archimedes did not really have the benefit of calculus at his disposal, but this is very much an idea that is rooted in calculus, in the sense that he's thinking, well, if you take the limit of the angle to 0, you get the circle. And the reason this is important is because if we have the area, we can get the value of pi. We probably well know, and it's one of the more famous equations out there, that the area of a circle is equal to pi times its radius squared. And by doing a little bit of algebraic manipulation, we find that pi is equal to the area divided by the radius squared. And if the radius is 1, then pi is simply equal to the area. So if you know the exact area of the circle, then you also know pi. So that's a good thing to know, because it's very important for the method I'm about to teach you. But here's an illustration of that, just in case you're having trouble visualizing it. And you can see here that each one of these circles just barely covers a sector of the circle. There's a little bit of leftover area in the sector, and the idea is if you shrink the angle, the area becomes much less, and you can fit more triangles in, and all of a sudden the area becomes much more accurate. Now, this, for people who have studied calculus, is not much unlike the trapezoidal rule, especially considering that a triangle can be thought of as a degenerate trapezoid. And indeed, that is much of what we're trying to do, is we're trying to cram an infinite number of trapezoids under a curve in order to get the area. But modern techniques go beyond these geometric methods. So we have a method from the 1500s called the Gregory Leibnitz series, and the idea is that by approximating the arctangent function, you can actually approximate pi as well. So the way that this works is that you have this alternating series here that yields the arctangent of angle z, or rather of z in general, because the arctangent yields the angle. And you can rationalize that because the arctangent of 1 is equal to pi over 4, then by expanding this series out, that you can calculate pi. Well, John Wallace did this, and he was actually a little bit ashamed of it in a way. He basically was saying to his colleagues, should I be ashamed of the fact that I have nothing better with my time to do than to calculate pi out to the 39th digit? But about a century later, John Machen actually found a better formulation for pi over 4, which converges much more quickly, and he was able to get about 100 digits out of that. Well, the state of the art now are these things called spigot algorithms, and in particular, we're showing one here from 1995 called the BBP digit extraction algorithm. It's that infinite series you see down below. And algorithms like this particular algorithm, in fact, has been able to find the pi to the quadrillionth bit, or thereabout, and modifications of it have been able to find it to even the second quadrillionth bit. These hold the records, and these are the guys that are basically known because they're useful largely because of the fact that you don't have to have all the previous digits. You can start off from anywhere in the sequence as long as it's known. So yeah, that is pi in a nutshell. But I was going to tell you about a method involving drinking, and you shall have that, in fact. So let's say you go out to the bar tonight, and you're out drinking with your friends. Maybe one of them is the designated driver and isn't drinking, which is actually pretty good for this particular experiment. Because you see, you're going to get so sloshed that you essentially become a random number generator. In the sense that, let's say you have a dartboard in your bar, and not all of them do, but some of them do, many of them do, and you are so drunk that when you throw the darts, you have an equal chance of hitting any one particular spot. Well, the idea is this: your sober friend is going to measure the number of times that you throw the darts towards a certain square area that is twice the radius of the dartboard. That is to say that this area is the perimeter is tangent to the circumference of that dartboard. And he's also going to, out of those times, determine how many hits you make. Well, this is useful to us because we can calculate the ratio of the area of the circle to the area of the square. The area of the circle is pretty easy. It's pi r squared. The square itself is, of course, 2r quantity squared. And that means that the ratio of these two is pi over 4. And so if you think that in a uniform uniform sampling that these guys, that the ratio should be approximately equal, then we find out that pi is equal to 4 times the number of hits you make over the number of darts thrown. And you can see that illustrated here. I do want to point out that random sampling is it's sort of a requirement here. If you had a normal distribution, you might expect these guys to cluster up somewhere, perhaps in the center, and that would give you an invalid measurement. But you can see basically the idea is that we're expecting the circle to take up most of this area, and then we're taking out the remainder of the the remainder of the square as a result. So this is a process called Monte Carlo integration. It actually came out of research out of the Los Alamos laboratories. Fermi is thought to actually have been the first person to utilize it, but the at Los Alamos laboratories, this is thought to have been pioneered largely by John von Neumann. And basically, the idea is that you have the dartboard, except the dartboard can be any curve, any closed space, or whatever. And so, the idea is that because you're doing uniform sampling, the sampling ratio should be fairly close to the real ratio. And because the radius is 1, then pi must equal that ratio. In fact, it would equal it irrespective of the radius, um, just as long as, the square was tangent to it. And so there we have this formula for Monte Carlo integration, that if we have some function f of a vector x, then if we integrate it with respect to volume over some sample set theta, then that is equal to f over the approximate application of the approximate average application of theta to f. Kind of a weird thing to say. All of this domain theta here is in domain of this vector x. So as you can imagine, the more samples you have, the better. So it turns out that this is actually very easy to simulate on a computer. And in fact, it's a good sort of practice case for learning how to do parallel computing, because the more samples you have, the better your results usually, notwithstanding things like floating point error and things like that. And so if you can imagine one drunk, performing this, imagine what would happen if you had thousands of drunks independently doing this with thousands of dartboards. Well, you can simulate the drunks with a uniform pseudo-random number generator of your choosing. So, when I did this, and yes, I actually did do this on the video card, I managed to get about, I think it was 20 or 30 gigasamples a second, and that was using the linear congruential equation, which I might post a link to Wikipedia for that, or maybe Wolfram. And then your dartboard is the circle inequality. You have this parametric equation where you have your x and your y, and this is essentially equivalent to the Pythagorean theorem. And so the nice thing about this is that because the drunks don't really have to talk to each other, then you can more or less do this in with very, very high speed up, because the main thing that puts the limit on speed up, or really in fact the only thing, is the amount of serial processing you have going on in your process. That is, the amount of time where everybody waits for one person to complete a step. So that really only happens whenever you're combining all of the results, all the counts, so to speak. And so for that reason, this has been known as embarrassingly parallel. So just a few closing remarks. Monte Carlo methods aren't just useful for calculating pi. As you could probably figure, Monte Carlo methods are, in terms of its integration method, is useful for just about any volume or hypervolume you can think about. And an extension of that, Monte Carlo Markov chain methods are actually used in for things like sequence and structure prediction. So they actually used this sort of thing to model the structure of like RNAs, like the secondary structure, how shall I explain this? The physical conformation that these RNAs make, because without going too far off topic, these RNAs are kind of like DNA, and they do sometimes bind the individual bases bind to each other, and that gives certain RNAs catalytic activity. And so they model this sometimes using the Gibbs sampler, or they model other motifs like this as well. So this is a big bioinformatics thing. And then with respect to physics, and I suspect this was probably one of the original use cases for this sort of integration actually has uses in the n-body problem, and I believe this was actually developed for quantum mechanics. So, as you may know, if you have tons of bodies interacting with each other, the math gets kind of hairy. So, having this stochastic method really helps. So you could take this to the bar, impress your friends. It's kind of like teaching your drunk friends how to count on their fingers in binary, which oddly enough will let you count to 1024. It usually causes a little bit of tension after you get to the number 4, because of course your middle finger's up, but it's kind of fun watching, but it's also useful. It's really quite a way to celebrate Pi Day. Of course, don't actually get this drunk. You'll put yourself in the hospital with alcohol poisoning. And if you do decide to drink on Pi Day, please, of course, be responsible. Please call a cab if nobody can take you home. Don't try to drive home drunk, especially after this experiment. But this has been Thy Lord Root, and I will see you next time.